4 sections, and then we have a test over them. So I messed up the schedule. For some reason, I was scheduling us to meet on, Thanksgiving. We're definitely not going to do that. So the test is going to have to be the day that we come back from Thanksgiving. So please don't do horrible things to yourself. There will be a video up. There will be videos up. If you have to, like, put that video on like Monday afternoon or something like that. Recap it, like rewatch the video. Make sure you know what you're doing. We're going to go over the quiz on next week, next Tuesday, before we all take off. Or hopefully not everyone's taking off. Should probably be still careful about spreading stuff. But I know some of people are going to go and spend time with their family, and that's kind of your own discretion, right? Be careful. I guess that's all I can say, right? Here's my phone. The other thing, I put up the project. Did y'all get an email about that, or did y'all not click the email thing? Sometimes I probably didn't click it. Ooh. Let me fix this up so I can go. Let me go to my courses and not show sensitive information that you don't want everyone to see your grade is probably not the good thing. But here we go. It is in research project. So if you click on research project, it should open it up. But here is the research project, and I've kind of already talked about it. Basically, what I want from you, I want you to go research something. I want you to write basically 3 pages to me proving that you did some research. Go find something that like you enjoy, hopefully, something you find interesting. So let's read. Students are expected to research about a math-related topic. So I am pretty broad in general and like what I'm expecting here, I think, like topic-wise, as long as it has something to do with something math-related, and you hopefully find it interesting. Compose an essay to demonstrate the research and understanding of the topic. The following criteria. The really things that I'm going to be picky about is that it has to be like 3 pages. So if anything, it should go over into like a 4th page, right? A lot of people are turning in like 2 3/4 of a page for 3-page. Like you're not going to pass. When I took other classes, I would not be passing that class if I turned in 2 3/4 of a page. Like that's automatically like less than a 70 usually.
Are we double spacing this?
Yeah, it's MLA format, double space, Times New Roman, 12-point font. The standard sort of stuff like when you write any other paper. It needs to be in that format so I can kind of see how long it is, right? If you're doing anything else, like I'm probably going to drop you down to something lower than a 70. Like these are the things that I'm going to be really strict on. And then you need 3 scholarly sources. It's got to be 3 pages. You should typically have source per page, I think is usually what's required, something around there. To find like 3 sources, you don't necessarily have to pull like equally out of all 3 sources either, right? Like some people, I think, have that impression. You just want to basically, you want to be able to verify stuff, right? Make sure stuff isn't fake news, right? The irony behind that is the person promoting it is probably one spreading it the most. One of the ways that we verify sources is to make sure that they are consistent. Like we have consistently the same story, right? You don't want just to like pick some oddball that wrote his own story out there that makes no sense. So consistency is a big sort of thing if you want to verify a source. So that's also like you might be saying the same thing, right? The 3 sources might be saying the exact same thing, but still you want to pull at least like 3 sources. Make sure you get like a consistency of information. The other thing that we do in like scholarly research is like we like to cite sources because if there's something wrong, it's not our fault it's wrong, right? It's the source's fault. But you only take responsibility for what you're doing, right? So to speak, and you don't take responsibility for other people. If other people are misleading you, that's part of the reason why we cite stuff. Is like if I said something misleading and it was based on something that someone else said that was misleading, it wasn't my fault for saying it, so to speak, right? It was more like their fault for spreading it. So a lot of this and like a lot of like citing your sources and stuff is just taking responsibility for your own actions and not taking responsibility for things that aren't your own actions, I think. Okay, so I think that's pretty much it. The rest of it are kind of just like some topics that you could report on. Oh man, I know I'm gonna get like 100 papers because I put this on there. Like everyone does the history of zero for some reason. I guess it is a pretty interesting concept, and I'm not gonna totally knock it. But like almost everyone and their dog like tries to report on zero. The history of irrational numbers, you probably may not find as much on that. Factoring cubics, Cardano and Tartaglia had a feud, so if you want to do anything on them. The Leibniz Newton, who invented calculus sort of thing. I think I'm going bottom up. The applications and importance of mathematics in your profession. If you want to like, if you want to go do some extra work and interview people and come up with interview questions and stuff like that might also be a valid sort of way to go about this. If you really wanted to do that, we could talk about that. Or you could talk about a mathematician. So I've listed some notable mathematicians. Did I talk about the Nobel Prize? I think so. They don't have the Nobel Prize in math, right? It's called the Fields Medal. Miriam Mirzakhani, I guess is, I don't ask me if that's the correct pronunciation, but she was the first female Fields Medal winner. She passed away fairly recently, but who else? Ramanujan learned how to do math in the dirt. Russell and Whitehead, they were, I think Whitehead was of the Vienna Circle. They were all of that era sort of thing, doing logic. So I should probably not tell you that, because now you're not going to do him. Erdős was a pretty interesting guy. He was Hungarian, Jewish Hungarian guy. He traveled and did a lot of math. He is the most prolific mathematician, right next to, oh man, who's the other one? Next to Euler. I think Euler beats him. But if you do on conjoined papers that were done in conjunction with people, I think Erdős like outdoes like everyone. I think Euler had more independent ones, but like Erdős outdoes everyone. He used to like travel around and just like match sort of like math problems with a mathematician. His motto was a new roof, a new proof. He was really kind of eccentric, crazy. Avertis Gawa did some kind of crazy. Oh man, I can't remember. It isn't. You learn it in algebra.
Is that Eratos? Whatever. Of Serene.
Évariste
Is that what that is? Yeah.
Évariste.
Yeah,
Évariste Galois. He like died.
No.
He died before he was 20. Carl Friedrich Gauss, Ada Lovelace, Muhammad. This one, Muhammad.
No,
Ibn.
His name is Eratosthenes of Cyrene.
Oh, you're way ahead of me. Euclid. Euclid's
at the bottom.
I know. I'm reading them in order. So this. Now we're starting like the Greeks, Euclid and Pythagoras and Hypatia and Aristophanes, the Cyrene, Archimedes. Cantor is not Greek. He's the other crazy guy. Zeno was also another Greek. If there's any questions, you can always ask me. If it's a valid topic to do, you can always shoot me an email. Any questions about this? What's kind of expected about your research project? And I'll set up the link for, I guess, to submit it. I guess I got to do that. I hadn't done that yet. But this is basically going to be due by like the last day by your final, basically.
Okay.
So I think, how many more weeks?
Like 3?
4. I think we got 4. Right? 1, 2. We got this week. We got part of next week. Yeah. If you do a page a week, I think you get it done, right? Something like that. Are we on? Yeah, we got 4 including Thanksgiving, so. I think it should be manageable. I don't think I'm asking too much. And this is worth a pretty good portion of your grade. I would have to look at the syllabus again to remember exactly how much. I think it was like 10 or something. Wrong class. Never mind. Yeah, it's worth 10%.
And as far as sources go, do you think we'll be able to find a fair amount of information through the ACC library website?
Yeah, so most of this is with your 3 scholarly three scholarly resources properly cited. Like, for the most part, going through the library, I think you should be able to find probably something on each of these. Even like, I know Wikipedia is not like a reliable something so you can cite on like for a scholarly source, but even like going to Wikipedia, most of these are like pretty common topics or pretty common people. You can go to Wikipedia and Wikipedia cites their sources. So you can look at the sources the Wikipedia cites. And those are usually valid resources or valid sources that they're citing. It might give you a direction too. I don't know. There's a lot of sort of like popular math, recreational math, Mathologer, and there's another one that's pretty popular. They might give you a direction to sort of go in as well if you want to look at something. Like I said, I'm not being too strict as long as it's something sort of math related. It could be math history related. It could be topic wise. It could just be a mathematician maybe, you know?
Okay.
I just want you to do a little bit of research and do some recreational math. I know it's kind of crazy, but okay. All right, so I think we probably need to get started on stuff. So far we, well, might want to connect it first. Sorry about that. So far we had a test last class. So there's not a lot we can go over or recap besides I'm grading a bunch of tests. And those will be back as soon as I get them graded. All right. Is that too slanted? I think it's all right, huh? All right, so 7A, 7B, 7A, we talked a little bit about probabilities. And so basically there is there's 2 sort of concepts, but they're really kind of the same thing, right? If we want to find the probability of some event, or A, it's the probability of the number of times the event occurs over the total number, right? Total number of possibilities or total number of outcomes. Possibility. If we're doing theoretical, we're talking about the total number of possibilities. If we're doing, I can't even think, frequencies, right? Relative frequencies, we're doing the number of outcomes that we did. We're conducting an experiment with the relative frequency. It is one and kind of the same concept. we're either doing it theoretically or we're doing it in an experiment and seeing what the experiment actually produces. But it's the same sort of thing. We're thinking about the number of times the event occurs over the total number of times that are either possible or the total number of times that we did the thing, right? Oh, this one's even simpler than that. We don't even need this principle yet. A restaurant has a special menu that features 2 choices of salads, 8 choices of entree, and 6 choices of dessert. How many different 3-course meals can you order? I'm thinking salad, entree. Right. How do I figure out the total number of combinations here?
Multiply them.
That's the multiplication principle. So there's two choices of salads by 8 choices of entrees by 6 choices of desserts. 16 by 6 is what, 96? This is like the Whataburger problem, right? When I was working in Whataburger, they used to have this sign that said there's like, and they gave the amount of number, right? It's like there's so many ways to order your Whataburger. This is basically how they did it. People are like, you must be some kind of math whiz to get that number. No, all you gotta do is multiply a bunch of things. So this we went over when we did like the logic, and I talked about it in the notes, like it's the roads problem. If you have 2 by 3 roads, how many different routes are there? If you have this many different options, we multiply the options to get the total number of options. Theoretical probabilities, use theoretical probabilities to determine. Did I like skip something? I feel like I skipped something in here. Yeah, maybe not. Determine the probability of the following outcomes in event state. Any assumptions that you make. Randomly selecting 2-child family with 2 boys. All right, so I probably like threw out every boy girl problem. I don't really like them that much. Reinforcing the dichotomy, there's either a boy or a girl is what they're doing. So if we have 2 children, what are the possibilities that we could have a boy and a girl for 2 children? Or what are the different possibilities for the gender, boy, girl, boy, or girl. So you're thinking every different combination for 2 different individuals. And so if we want to know the theoretical probability of selecting what, a boy and a boy or 2 boys, what is the probability of doing that?
1 in 4.
Yeah, it's 1 in 4. Okay. So that is theoretical probability. So out of a total of possible of what, 4 different outcomes, we could also do, we have a 2-child family, right? So the other thing was we could think about the multiplication principle if we didn't want to list them all out. If we have like child 1, child 2. And if we want to reinforce the dichotomy, there is either a boy or a girl, or there is either a boy or a girl. So there is a total possible 4 different combinations, right? So out of 4 of them, we're talking about one specific one, or a boy is going to occur once out of 4 total, right? One boy out of 4 total, right? So you're thinking about the occurrence out of the total, basically. Either you're doing theoretical probabilities and you're thinking about all the possible outcomes, or like I said, you're doing relative frequencies. Now we're going to conduct some sort of experiment or we're going to look at what happened previously, right? In the past. It's either observational experiment or like an observational study or experiment. That's what I was trying to say. And so 29 says, this would be like an observational study. The local weather forecast has been accurate 15 out of the 27 days. Based on this fact, what is the relative frequency probability that the forecast for tomorrow will be accurate? I haven't been checking these. So how do we figure that out? What's the occurrence out of the total is what they're asking, basically.
$15 divided by 27. Well, 15 out of 27.
Yeah, 15. Is that they're both what, divisible? Okay, so we can reduce this a little bit. They're both divisible by 3. I think. Just a little more clear. No, probably not. Okay.
Is there like an easy way to figure out how to reduce those kind of like weird fractions, or do you just know that by looking at it because you're a math professor?
Like 15 out of 27.
Yeah, do you just?
So if you have a calculator, it's really easy. There is this thing, if you go to math, if it goes to like frac or fraction, if you hit math frac, it will give you the reduced fraction. Other than that, it's being able to look at 15 and being able to do prime factorizations of these things. This is kind of what goes on in my head. I think about 15 and 3 and 5. I'm thinking about the factors of it. And what they have in common.
Okay.
So that would be one way to think about it. But I don't know if I'd break it down all the way to its prime factors. I might just stop there at 3 and 5 and 3, 7, because that's really the rule that we're using. Like 15 out of 27 is like those two things. And we can circle this thing, and it's just like you're multiplying by a big fancy 1 there.
Right. Okay.
Yeah, we're using that sort of rule, right? And we can reduce it to 5/9. There's something in common that they both have as a factor. Yep. If I want to do it real quick, I'd do it on a calculator though, probably. So sometimes it's not so easy. 15 and 27, I know those are both multiples of 3. So yeah, I probably did too much math. My brain's warped. Make a probability distribution for the given set of events. You may use either a table or a graph. I'm definitely going to use a table. The number of boys in a family with 3 children. How many different options should I have if I do have 3 children? How many total different?
Would be 8.
It would be 8 because for each you got 2, right? And if you want to do like boy girl, you can do it with a chart like this, right? Boy girl, boy girl. And each one of these you're gonna branch off. Boy girl, boy girl. This might help you get everything down. And then we follow the branches along. So if I follow the branch all the way up, it gives me B, B, B. If I follow this branch B, B, and then I guess I go down 1 to G, we can kind of sort of follow these branches B, 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 B. I start with the upmost one and I keep going down a little bit each time, right? B, B, no, did those. B, G, B, B, G, B, B, G, B, G, G. I think I did 4 of them. I did half of them GBB. Swedish I did one twice or something. I do. GBB, GBG, GG. No, not that one yet. Sorry, went out of order. I guess it didn't really matter as long as you get the 8 down. And then if I'm thinking about occurrences of boys, I can have what? What's the least amount of boys I can have, and what's the most? If I'm talking about 3 children,
0 and 3.
0 to 3, right? So if I go 0 boys, 1 boy, 2 boy, 3 boy. This one in your notes. I did. Probability of the event. So what's the probability that you will get no boys?
1 of 8.
Yeah, I think I did this one in your notes, didn't I? There's a different one in the book, I think, but I think I might have did this one in the notes. How many of the different ones have 1 boy in them? This one, and this one. So I think there's 3 out of them. If you count the 2 boys, I believe there's also what, 3 of those? 1, 2, and one of them over here, 3. And then 3 boys, I think there's only one way to get 3 boys. All right. How can you know if you did everything correctly? What's a good way to check this? No, I did something weird.
Everything adds up to 1?
Yeah, should add to 1. No, that's right. I didn't. Never mind. I don't know how to add numbers anymore. That's right. So 3 8s plus 3 8s gives me what? 6 8s, 7 8s, 8 8s. It should be 8 out of 8, right? If we add these all up. And so, well, here they don't reduce, right? But sometimes in your probability distribution table, these things will reduce, but like it is usually better just to keep them over the same number if we're going to have to do calculations with them. So this should be my table, right? I should probably make a better table out of this thing, but there you go. Are there any questions about this thing? I think we went over this in the notes already. Okay, so that's probably the distribution table. Odds. Oh man. So this, if I'm being honest, I wouldn't know this unless I taught this class. Odds against or odds on something. If we're betting 3 to 5, what this means is for every $5 we bet, we're going to make $3 back. Or we will be winning $3. So if we bet $20, how much will you gain? And I think it was like P of not A and P of A, the odds against. It's something like this. This is odds against A. So how can we think about this? If you're spending $20, how can you think about that like relative to 3 to 5?
It's 4 $5 bets.
It's 4 $5 bets. Another way you can think about that is I'm doing 3 to 5. 3 is the not A and 5 is going to represent the probability of A. I'm putting my money of what, $20 on that 5, right? So you can also do this with like an equivalent fraction. So I'm going to multiply to 4 to get there. I should be making what, 3 times 4 or $12 is my winnings, right?
When they say how much will you gain in these questions, do they mean including your original bet or just your?
That's about to be the next thing I'm gonna take get at. So I'm winning $12, right? So I should make $12 profit off of this thing, but I paid what, $5? No, I paid 20. Sorry. Yeah, I bet $20. So I already put in $20. So I also have to get $20 back. So when I go up to the window, this should be like my takeaway amount, right? So I'm not sure what they were wanting for this. Let me look right quick. This is 47. They say you're gonna gain $12. So they wanted the $12 here. In the homework or in the notes, they did something different. So you will be $12 up, which means you need to get a total of $32 from the window, right? That's how much your ticket stub should be worth. So anytime you go, for all those people in here going to horse races, there we go. Well, I guess you don't really have to go to the Derby to bet on them. They bet them on them everywhere, kind of, if you got a bookie, right? Okay. So that was 47. What does it say? Computing probabilities, decide which method, theoretical, relative, or subjective, is appropriate, and compute or estimate the following probabilities. If you use subjective method, explain your reasoning. Not hearing your favorite group of random shuffle on your playlist that has 889 songs, of which 127 are by your favorite group. So I know they probably just want a method, but like we're probably gonna go and solve it, probably even. Oh no, they want it. They want the number 2. Okay. So is this a theoretical or relative or subjective? If you tell me subjective, I'm gonna cry a little bit in my heart. Subjective is like one of those things like I think you're gonna get married next year or some bull like that. I don't know. Like it is not something that is really based on a number. It's something that's based more on like intuition and what you feel. We're probably not going to talk too much about subjective, but it exists, right? I'm going to want you to crunch something in this class, probably. So is this theoretical or is this relative?
Would it be theoretical?
Yes, it would be theoretical because it's not actually, you're not actually looking out of the total number of songs that played. You're looking at what? 127 are by your favorite group. So there is a little bit of like maybe handwork we need to do. If 889 songs are the total, and these are the total possibilities, right? So these aren't the total possible, what was I saying?
The possibility of the 127 playing is not possible. It's theoretical.
These are possible outcomes. They're not, what's the other word I was using? I'm looking at my words consistent as well as well. No, these are the total possibilities. These aren't the outcomes of something that's happening, right? That's what I was trying to say. I was using the wrong word, which is why it doesn't help. So these are the total possibilities. These aren't like we're letting things play, right? And then seeing how many songs that played, how many of them came up. We want to know the theoretical probability of not getting your favorite song or your favorite group. So one thing we might have to do, and there are multiple ways to go about it, but if 127 are by your favorite group and we have 889 total, then 762 are not, right? Meeting. So what is the probability of not getting your favorite artist playing? Theoretically. Or you could figure out what the probability is of getting your favorite artist and do something to that. There are 2 different ways to sort of get this one. So out of the total songs, what occurrences are not my favorite artist?
Six and seven. Oh, well, that's reduced already.
So the 762 is with that we're not receiving.
Huh?
So
Out of total of how many?
762.
Out of 889.
Out of the total of 889. So this is the probability I'm not going to get my favorite artist. This is the occurrence of it not being my favorite artist out of the total number of songs that I have on my playlist. So if we do 762, 889, you're saying what, 6/7? Is
Yeah.
what this thing reduced is?
Yep, 6-7.
Or you could do 8/5 maybe. 8/5/7.
Professor, I got a question.
Oh yeah.
So for this one, the way I solved it, I used the probability of event not occurring. And I still got the 857. Would that be just as correct?
Are you talking about, so there's another way. If I do 127 out 889, this gives me the probability that I will get a song from my favorite artist, right? And then did you subtract that from 1? Is that what you're doing?
Yes, sir.
Oh, that's exactly what you want to do. So this is going to give you 1 minus what? 1/7, which will give you the 6/7. So you can do 1 minus the probability it will occur, right? And it will give you the opposite. Because you're either going to get a song by your favorite artist or not your favorite artist, right? So they should add up to 1. We can use that fact, subtract this from 1 to get the other half of that, right?
And I got one more question. Could you show me the button on your calculator that you went to the not fracking or the not frac or the whatever that was that you did?
If I do like 762 over 889, is that what you're talking about?
Yes.
It's under math. Usually if it's math, it's this little thing that says frac. But it might be somewhere else depending upon your calculator. You can just enter frac and it converts your answer to a fraction, a reduced fraction. And you can
Okay.
also convert it back to decimal. If you want to go from fraction to decimal, it's got a little decimal thing in there too.
Okay.
Okay, I see. I have that button on mine. Thank you.
Yeah, I'm using degree, Professor. So I still got 0.857.
Ah, that's it.
Okay.
Ooh. Now we're gonna draw marbles. I feel like this one's in the next section. Remember like crossing stuff up here? Or is this it? And that's it. 67 and 73 are the last two in this section. And this just sounds like one that should be in the next section is all it is. Because they're giving you multiple things now. Suppose you reach in and draw 2 marbles at random from a bag containing 10 white, 10 black, 10 red. List all possible outcomes of this process. Ooh. How many different ones should we get? That's the first thing you should probably ask yourself. How many different outcomes? B. Bull. Sorry. How many different outcomes can we get for our first marble when we draw it? There is either red, white, black, or red. So how many different options does that give us?
3.
Yeah. And how many options do we have for marble 2?
3.
Same
3.
thing. And how many total options do we have?
30 or 20? Is it 20? Is it? Wait a minute.
What are y'all doing?
Wait a minute. Hold up. 3.
3 by what?
10. 10. 10. 10.
So I got 3 options
30.
here. I got 3 options here. How many total options do I have?
6.
6.
Woo, man, what's the operation here? Yeah.
Wasn't there a third marble?
Multiplication.
9. It's 9.
It's 9. 3 by 3, right? This is either white, red, or black. This is either white, red, or black. If I combine right, red, black, and with right, red, and black, I should get a total of 9 combinations of these things. It should be 2-letter combinations. So I'm doing white, black, and red. WBR. First thing, I can do white, black. I should start with white, white, probably, right? The same thing. What I'm going to do is hold one constant. White, black, white, red. You could do it with a chart if you really wanted to. White, black, red. Oh, sorry. This is my first marble I draw. I have 3 options. This is my second marble I draw. I have 3 options. Each of these branches, I'm multiplying each of my option, right? So this is going back to the multiplication principle. If I got 3 options and 3 options, I got a total of 9 options. So I think I'm doing this white, 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 black, right, white. I'm gonna I'm gonna sound like a Three Stooges for the rest of the class, I guess. Or is that more Bugs Bunny? I'm not sure. BR, RW. So these are all the 9 different combinations. Get them all on there.
Okay, so what I had was white, 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 black, and white, red. Then
Mhm.
black, white, black, red, and black, black. And
Yeah,
then
that works.
red, white, red, black, and red, red.
Yep.
Okay.
I think you just swapped them 2 or something, but it's the same thing. Just different order. It's the same. We get 9 different combinations is what you should be getting. So list all possible outcomes of this process. These are all the possible things. If you want, like maybe making this branch sort of chart might help. This is like marble 1. This is like my marble 2, right? And if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, that will tell me there's 9 options. If I follow the branches, I can get each of them, right? Okay. So I'm hoping if I give you different options, this is picking 2 marbles. It could be like flipping a die, right? Or flipping a coin and rolling a die, right? If I want to do that, how do I do that? So how many options would I have if I flipped a coin and rolled a die? And I recorded the result. So how many options does a coin have?
2.
2,
2. And how many does the die have if it's 6-sided?
6.
6,
6. So how many different options would there be?
12.
12, right? I'm gonna think about it. Tails and heads. 1, 2, 3, 4, 5, 6. Or I could get a heads in 1, 2, 3, 4, 5, 6. Sorry, I'm being really sloppy with my little T chart or whatever, my branching. But then if I count them up, there'd be 12 different options. Like, I really hope y'all can do this sort of thing. Like, this is something y'all should be able to do, is like list the options of these sorts of scenarios. If you got to do your little branchy chart, T1, T2, T3, right? T1, T2, T3. I don't want to list them all out, but I'm going to list them T and a number. I'm going to list H1 all the way to H6, right? You should hopefully be able to do something like this, right? I'm hoping you all understand this. Make a table or graph showing the probability distribution for the events of 0, 1, and 2 black marbles. So back to our marbles. Don't lose your marbles. Yeah.
Ha ha ha.
Black marbles, right? Marbles. 1 black marble, 2 black marble. Marbles. This is the event. And so we're picking 2 marbles. So the least we can have is 0 black marbles. The most we can have is 2. Now I want my probability of my event. What is my denominator going to be on all of these things, hopefully?
9.
9. I mean, yes. Yes, 9. Sometimes 9 means no. WB, we want to do 0 black marbles. How many of these options have 0 black marbles? 1, 2, 3, 4. Does that seem right? I think there's 4 of them. How many have 1 black marble?
3 is 3. It's like
1, 2,
white, red, and
3, 4. I'm seeing 4.
white.
1 black
white,
marble.
Red. I'm sorry, white, red. Yeah.
We got 1 black here, 1 B here. 1, 2, 3, 4 of those. And how many ways are there to get 2 black marbles? That one, if you really want to look at your list, there's only going to be one thing with 2 black marbles. There's one way to get the same thing twice. And if we did this, did we do it correctly? Can we check it? Check it. Does it check? How do you know if it checks?
You add all the
4 nights plus 4 nights plus 1 night. Does that give me 9, 9?
Yes.
9 nights, which is the number 1, right? Is what I'm saying. Same thing over itself is always 1. Except for we're not talking about 0, but that's a different story. But any number that's not 0 over itself is 1. All right, so I think, is that the final problem for this one? No, one more. Gender politics. So they're grouping people by Republican, Democrat, Independent, and whether they are male or female, man or woman. And so if we look here, this would be what? A woman Republican. This would be a woman Democrat. This would be a male Democrat. This would be a male Independent over here. So what is the probability that you meet a man? So if you add all these numbers up, hopefully they didn't mess it up. 21 plus 28 plus 25 plus 16 plus 6 plus 4. Did they really mess that up? 21, 28, 25. Oh, never mind. I messed it up. 16, not 26. Woo. If we add them all up, we should be getting the 100 delegates, right? Is what they're doing. There are 100 people total is what they started telling us off with. So there is 100 people total. If we sum these guys all up, we're going to get 100. So what is the probability that you meet a man?
48%.
48%. And where are you getting that from? You're looking down probably this column right here. You're adding up 28 plus 16 plus 4. And 48 out of the total of 100, right? This is what it sounds like to me. What is the probability that you will meet a Democrat? I can't even speak anymore, but there you go. What's the probability of a Democrat? So now instead of a row, I think we're looking at a column. Are they expressing it as a decimal? Typically, you express probabilities as a decimal. I'd say 0.4. And usually it's a number between 0 and 1. Sometimes it makes more sense to express the probability as a fraction. It's one of those sorts of things that you might have to look at the context and figure it out. So how do you figure out Democrat? What 2 numbers are we adding?
25 plus 16.
25 and 16 gives me 0.41. Looking at that 41, which is 41 out of 100.41. What about independence? That's going to be point what?
0.9. It's, you do not meet an independent. Oh, wait. Yeah.
6 and 4?
10.
Yeah, it should be.
Yeah, but the probability that you do not meet an independent.
Oh, do not meet. Oh, whew. That is a good thing to catch there. So the probability that you do meet a independent is going to be 10%. If we want to know the probability that you do not meet one, how would I figure out the probability I'm not going to meet one? We could probably sum up all the other people and do it that way if that's what you did, but I wouldn't personally do it that way.
1 minus the number of dependents
I would do
over 100.
1 minus this is what, 90. So if there's a 10% chance that I'm meeting them, there's a 90% chance that I'm not going to meet them, is what this is telling me. What's the probability you will meet a male Republican? So what number am I looking at here, or what numbers am I looking at?
28.
I'm looking at just a single number, 28. So this will be 28% or 0.28. And what is the probability you meet someone that is not a female Republican? So this says not a female Republican. Typically, I would not do the not. I would do, what is the probability of meeting a female Republican? That would be the easier thing to find. Oh man, the sound just like dropped. I think my AC kicked off or something. And went silent. So how do I find the probability of meeting a female Republican? What number am I looking at?
21.
I'm looking at the 21, and I don't want to do that, so I am going to subtract that from 1. So 1 is like 100%. It's guaranteed to sort of happen. So I believe it should be 0.79 on that guy. Any questions over this table? So we're doing them all over the total of 100, so that makes it probably a little bit easier to convert to decimal. Okay. So that is the sort of basis of probabilities, right? How do we find a probability? How do we find it theoretically? How do we find relative frequency when we're actually conducting an event, right? Now we're going to talk about how do we combine events? How do we combine them with like phrases like and? How do we combine them with things like or? If we're doing and, can they happen at the same time, right? We got to ask ourselves, is there overlap in them? Is one influencing the other? So when we do and, we have to look at whether they are dependent and independent. These are the words I was trying to think. And we have to think about whether they're independent or dependent. And when we do or, we have to think about whether they're like mutually exclusive or overlapping events, right? Have I used these words before? I think probably when I did that logic, we talked about overlapping sets versus mutually exclusive sets. With that said, decide whether each of the following statements makes sense or is clearly true or does not make sense, is clearly false. Explain your reasoning. So we got two different statements here, 5 and 7. The probability of getting heads and tails when you toss a coin is 0, but the probability of getting heads or tails is 1. Does that make sense? So if they say the probability of getting heads and tails when you toss a coin is 0, is that true? Is it possible that you could get heads and tails if you toss a coin?
No, you only get one of them.
Mm-hmm. Okay, so yes, yeah, okay, yeah, okay. Now I see what they say. This is a kind of a weird phrase. They're saying you're tossing one coin. Is that what it says? Yes, they're saying a coin, a single coin. Is it possible that you can get both heads and tails if you do a single toss?
No,
It's not possible, so that's like saying the probability of it is
0.
0. But if you're going to toss a coin, is it true that you're going to get a heads or a tails?
Yes.
You will get one or the other, right?
Yes.
This is the either or. You're going to do one or the other. And so it's guaranteed. So it's like you have a probability of 1. So it's kind of a weird way to ask it. But this should be a true statement. It should make sense. So and means we're doing both of them at the same time. Or means we're doing like one or the other, right? It's coming out one way or the other, but not both. Okay, so the probability of drawing an ace or a spade from a deck of cards is the same as the probability of drawing the ace of spades. Is that true?
Okay, that's false.
That is definitely false. So if we think about an ace or a spade, how many cards am I thinking about there?
With 52 cards in the deck, so if you get
So
an
how
ace,
many
there's
are-
only 4 aces in the cards.
There's 4 aces and there are what, 13 spades?
Oh yeah, 13 spades. That's right.
So if we think about how many cards are either an ace or a spade, here's 4 and here's 13. But what I really have to do is I have to do 4 plus 13 minus 1 to account for the fact that there's an ace of spades that's in common. So there would be 16 cards total that I'm really talking about here. Here I'm really talking about, I didn't say it, but it's an ace and a spade, right? Is the way that we say ace of spades. This would be like an and statement kind of hidden in here. But this is definitely false, right?
Yeah.
Here I'm talking about 16 cards. Here I'm talking about 1 card, right? And we kind of talked about like this or kind of unions the sets together. It builds the sets up. It makes the sets larger. This and we're talking about the intersection of things, right? We're talking about where the spades intersect with my ace. So I laid it out in your notes. Let's see. I try to lay it out like with this sort of picture. Remember this thing? And if I circle the set of aces and I circle the set of spades, the intersection or the and thing will be the ace of spades. Versus if I circle like 2 sets of suits, they're not going to intersect, right? So I could do something like that. Oh man. So with that said,
So drawing a heart is 1 out of 4.
yes, it would be 13 out of 52, which reduces to 1 out of 4. We kind of make, I'm just going to make it a little bit of tangent, but we kind of make assumptions that like, you know, people are just going to be familiar with these sorts of things. But like I've had experiences with people from different cultures, you know, we going to a college where people from all over the place, all different cultures and all different experiences come together, and not everyone has experience with playing cards. And I don't know, I've had students that have like never seen a playing card before, and then you try to explain the organization of them. You know, it definitely gives like certain people an unfair advantage in this class to have experience with them. And others have an unfair disadvantage, right?
Yeah, that's just a poker probability right there that you just showed. I know people don't play poker and all. I do, and I just seen that and I was like, yo, that's poker.
Yep. All those poker probabilities that they get. This is how they do them, right? But doing ands and ors, right? You get this and you get this and you get this. We can do the probability of getting a certain hand by doing and statements. And we talked about it. If you do and statements, what are we doing with the probabilities with and statements? If they are independent events, well, even if they're not independent events, we're just gonna have to change things. But like, what is this? What is the approach? Like, I take the probability of first event, probability of second event.
Multiply.
I multiply the events. So if I'm multiplying fractions, are things getting larger or smaller? And is it making sense? Hopefully. If I'm multiplying fractions, I'm taking fractional amounts of fractional amounts. I should be getting smaller. And if I'm saying things like, and I want to get a 5 heads when you toss a coin, I want to get a head and 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 a head. Would you expect it to be larger to get 1 head on a single flip, or would you expect it to be like smaller to get like 5 heads in a row? Like, this is really demanding, right?
Isn't flipping a coin like 49 to 51?
What are you saying?
Like if you flip a coin, it's not exactly 50-50.
Oh
You
yeah,
have-
yeah. Most coins
So
are not.
so the probability is sometimes 2 out of 5 or 3 out of 5 that you'll get your head.
Nah, I mean, we're assuming things in here. We're making the assumption that things are equally probable, right?
Oh,
Making sure
okay.
it's we're assuming things are a fair, even coin.
Okay.
In reality, things aren't fair and even.
Yeah.
And you might actually be correct. It might actually be more like 49-51. There might be a slight advantage to one side depending how the coin is weighted. Absolutely. But we're making the assumption that things are fair in here.
Okay.
And so if we want 5 heads, if we want to do 5 heads in a row, or we want to toss 5 coins and get 5 heads, what is the probability that's going to happen? The probability of getting head on your first one is going to be how much? If it's
2.
fair?
Just 1 out of 2.
1.
Yeah, 1 out of 2. And then getting a head on another coin, it's going to be the same probability for each head, right? The probability of getting a head on a fair coin is going to be a half. For each independent trial, it's always going to be a half. And we'll talk a little bit more about that with like the law of large numbers in 4C, about like doing the independent trials versus the overall sort of thing and how those relate. But I've kind of already said it. If I want to do this, the operation I want to do with my probabilities is all multiplication. So this should be 1 over 2 times 2 times 2 times 2 times 2. 2 to the 5th is, that's not 32, is it? Or am I off? 64?
It's 32.
Okay. So 1 out of 32 times. So do you want to list all those 32 possibilities? Probably not.
So just to clarify again, should we be, when we're giving our answer, should it be in decimal form? Or if it's a clean fraction, can it be a clean fraction?
If it's a clean fraction, it's fine if you put it as a clean fraction 1 in 32.
Okay.
It might make more sense, like, because this is saying the same thing as this is saying, really, right? And so usually we like to think of probabilities of something like 0 to 1. And it's just a format thing. Being able to recognize that this is a number between 0 and 1, whether it's written as a fraction or as a decimal, might be an issue with some people, right? If they see a fraction, they may not really necessarily know right off the bat, right? That it's, you can tell because if it's over 32, it's going to be over 1, right? 32 over 32. So I guess The more astute people probably pick up on that, but some people might struggle with it. And just to recap, like 0 means it's never ever. 1 means it's a guarantee, right? It's guaranteed to happen. It's 100% or 0%. We can think of it as a percent in decimal form is another way to sort of think about it. So this would be like 3% of them, a little bit over 3% of the time. 19, if we randomly draw and immediately eating 3 red M&Ms in a row from a bag that contains 10 red and 30 total. So we want to draw and then we want to eat them. Is it? Okay. And I didn't ask it here. I kind of just put it down, but like, does flipping 1 coin affect the flip of the 2nd coin? Does it affect the flip of the 3rd coin? So these were all independent events. We're talking about flipping a coin, like that's not going to influence the next coin. It's not going to influence this coin. My probability is always going to be 1 out of 2 to get ahead on any coin that is fair out there. My probability of getting ahead is a half. They're not going to influence each other. If I pull out M&Ms from a bag and I eat them, we want to know the probability of randomly drawing and immediately eating 3 red M&Ms in a row. Is drawing the first M&M going to influence the draw of the second M&M? I guess is my question. Are these independent or dependent?
Would it be dependent?
These are going to be dependent. Okay. I feel like a stuttering in my speech there or something. Dependent. Okay, so we want to think about drawing the first M&M. Drawing the second. And we're going to draw it. And if I'm drawing my first red M&M, I have 10 red out of 30 total. This one I'm hoping should be the easy one to get down. There are how many out of how many? If I'm drawing out of this bag and it's a fresh bag.
10 out of 30.
It is 10 out of 30. I draw my first M&M, my red M&M. I eat my M&M. This is going to change the probability of drawing a second red M&M. How is it going to change that probability? What is my total going to be now?
29.
I'm going to do 29 M&Ms total. And if I want to draw a second red M&M, how many red M&Ms do I have in the bag now to draw from?
9.
This one also goes. And then I draw that second M&M, I eat it. How many are left in my bag now?
8.
28.
28.
And how many red M&Ms are left in my bag?
7.
Going down 1.
8.
It should be 8. So this is the probability of drawing the first red M&M. This is the probability of drawing the second red M&M, given that I've drawn that first red M&M. So this is like that probability of A. And then it said probability of B given A or something like that. So if they are not independent events, we have to account for that, right? There's like B given A, and then there's C given A and B, right? Where A is drawing your first red M, B is drawing your second red M&M. C would be the drawing your third M&M. So if one is influencing the other, usually it's going to be like we're drawing something out of a bag without replacing them. We're going to eat them without replacement. Sometimes they will say replacement? I'm getting tangents in my brain and I like stop spelling words in the middle of writing them. It's bad. Don't do that. It says without replacement, just for anybody wondering. Okay, so I didn't do this yet, but what am I doing for these three probabilities? I want to do this thing, and I want to do this thing, and I want to do this thing. So on top, I have 10 times 9 times 8. So it should have what, 720 on top. And I set it 28. 30 times 29 times 28 gives me 360. I'm doing 720 over this number. Like 6 out of 2 or 3. This one might be a little bit prettier to give the fraction of 0.0296. Round it up. 0.296. So you can see it's around what, like 3%? Somewhere in that ballpark.
So Professor, I got 398. So I divide the 3 and the 98 again.
I don't know where you're getting 398 from.
Okay, so I did 1030 times 929 times 828 gave me 398.
I don't know why it's giving you that. It's 10/30th. It should not be giving you a whole number. Those are fractions.
10. Oh. 10 times 9 times 8. Oh, okay.
Okay.
Yeah.
So on these and probabilities, we want to think of whether they are dependent or independent. If they are independent, we just look at the probabilities separately and we multiply them all together. If they are dependent, we have to figure out how they are influencing each other, right? 21, selecting an all male 5-person jury from a pool of 10 men and 10 women. So you have 5 people. So if I'm drawing from this pool of people, what is the probability that I'm going to draw a male out of this pool of people? The first male that I draw out will be what? There's 10 men and 10 women. There's 20 people total. How do I figure that out?
10 out of 20 or 1 and 2.
Yeah, it'd be a half or 10 out of 20. I think I would want to go with 10 out of 20. So if I start pulling people out of this, am I going to put those people back? No. So is this independent or dependent? Is this one going to change because of this one?
Independent.
Is this one going to change because of this one?
Dependent.
This one's going to be dependent. It is absolutely going to change because of this one. I pull out a male. Now I'm going to draw out of how many people total?
9.
19.
19, yes. And each time I'm going to go down by what? By a single person, right? So I'm hoping y'all see this pattern, right? I'm going to pull a person out each time. And what should my numerator look like?
Is it going to be decreasing by 1 as well?
It's going to be decreasing by 1 each time as well. I'm going down by a single male, right? I'm going to males to total is what I'm doing here, right? And I'm going down to what? 6 over 16. So 10 times 9 times 8 times 7 times 6 gives me 30240. I'm doing that over 20 times 19 times 18 times 17 times 16. 1860480. If I divide these two numbers, 3240 divided by that crazy thing gives me, let's see the fraction, 21. I do the reduced fraction, it's 21 over 1292, which is somewhere around 0.1625. So we're talking about a little over 1.6%. So is it likely to happen? Not very likely, but does it happen?
Yes.
Can it happen? It absolutely can happen, right? Things that are improbable do happen, right? They do happen, they just don't happen very often. Okay, 23, get a sum of either 2, 3, or 4 on a roll of 2 dice. Ooh, so we might want to go back and look at that picture. Where's that? There you go. We had this in our notes. If we want to sum up the two dice, we're rolling 2 dice. So there's 6 by 6. Guess how many options there are?
36.
There are 36 different options in here.
6.
Some of them are the same. Some of them give you the same sum, right? 2 and 1 is going to give you the same sum as 1 and 2. But we want to do getting a sum of 2, 3, 4, or 5 on a roll or dice. Okay. So there are probably a few ways you can think about this, but if we're doing or, we want to know if they can intersect, right? Is the question we're kind of asking ourselves. Can these occur at the same time? Can we get a sum of 2 that at the same time get a sum of 3? Can these occur simultaneously? Getting a sum of 2 and getting a sum of 3 at the same time?
No.
No, right? Like it's either going to sum to either 2 or it's going to sum to 3, right? Or it's going to sum to 4 or it's going to sum to 5. If we add up 2 numbers, we're going to get a definitive sum. So if we roll a 2, 3, 4, or 5 on a roll of dice, are those overlapping or are those? So we kind of said they're mutually exclusive, right? They're not going to occur at the same time, is what we're saying. So if it's mutually exclusive, just means it's not going to occur at the same time. Overlapping means it can occur at the same time. So I think we're looking at 2, 3, 4, and 5. What do we do with those probabilities? So I get 1 out of 36.
We multiply all of them. No.
So this one we're saying or now.
So we're adding it.
So we're adding these things. We're doing 1, 6. We're adding 2, 6. 2 out of 36. Yeah, 2, 3, 4, 5. 2, 3, 4, 5. Looks like 1, 2, 3, 4. That is what we're doing. So I'm adding these 4 numbers. And this is where I was saying, like, it might actually help you to keep it with the same denominator sometimes. Because now these are all out of 36. We don't have to find a common denominator. But if I go 4 and 3 gives me 7, 8, 9, 10 out of 36, I think is what I'm doing. So one of the cheap tricks to reducing fractions is if they're both even, you can go, what, 5/18, divide them by 2. Usually dividing things by 2, 3, 5, if you start with your primes, I think you usually get them worked down pretty quick to things manageable. And this is problem what, 23? What did I say? Non-overlapping 5/18. Is that what I said? They say non-overlapping in the book, I think is the vocabulary they use. That is the same thing as saying events are like mutually exclusive. They're not going to occur at the same time. That's the same thing, right? I've never played craps, so don't even ask me. Next question. I have no clue. I think they explain it in the book somewhere. Drawing either a black ace or a red king on one draw from a regular deck of cards.
Okay.
So a black ace, what is the probability that you will draw a black ace?
1 in 52.
How many black aces are there?
I mean, I'm 4. It's 4. I'm sorry.
No.
2.
There's 4 black aces and
No,
4
there's
red
two,
kings.
there's 2 black aces, there's 2 red aces.
No, there's only.
Yeah, ace of club and ace of spade. Or 2 black aces.
Okay, I'm thinking. Okay, my
Yeah.
bad.
Maybe go back and look at that chart, right?
Yeah.
There should be 2 black
ace.
aces out of 52.
Yeah.
And there should be what? How many red kings? I think same thing, right? 2 out of 52.
There's 2 red kings. Yeah.
And so if we want to know, are these mutually exclusive? Can we have a black ace and a red king at the same time? Can you have an ace and a king at the same time even?
Yes.
Yeah.
What? A card can be an ace and a king at the same time?
Oh, no.
No. So those things, these things are mutually exclusive. So if they're mutually exclusive, we can just go add them together willy-nilly. We don't have to think about them being the same thing. We don't have to think about the overlap. We will get to a problem eventually, and it might make more sense. Why I'm asking if there's some overlap there when we finally get something that does have an overlap. Drawing either a 10 or a heart from a regular deck of cards. Ooh. So what about this? If I draw a 10, what is the probability I would draw a 10?
4 out of 52.
There are 4 out of 52 10. And what is the probability I will draw a heart? You can do 1 out of 4 if you want. But I think maybe doing 13 out of 52 might be better on this thing. So there are 13 hearts out of 52 cards. If I add these two together, I will get 17 out of 52, and you will be absolutely partially correct. That's not all of it. What do I have to count for?
The 10 of hearts.
The 10 of hearts. So here they can overlap, right? Is what the point is. And this is sort of like going back. I have to subtract what? The probability that it will be a 10 in a heart. Probability of 10. The probability of hearts. The probability that it will be 10 in a heart. You have to go back and you have to go and subtract that overlap. So what is the probability that I will draw a 10 of hearts?
Is that 1?
It's 1. There's 1 10 of hearts in the entire deck out of the 52. And so you can go back and you can think about like kind of your set or how many are going to be in your set. But if I circle my 10s, I circle my 10s along here and I circle my hearts along here, guess where they're going to intersect? They're going to intersect at the 10 of hearts. So if I count this 13 up and I count this 4 up, guess how many times I've counted this 10 up? I've counted it twice. So I have to subtract it. So if you count up all the cards, like all your hearts and all your 10s, there should be 16 of them total, right? There's 13 here plus 3 more. So it goes back up to the fact that if you add this set and you add this set, you end up adding that overlap twice. You have to subtract the overlap away, right? That's kind of what we're doing here. We're adding up 4 from this set. We're adding up 13 from that set. Hey, we've added up our middle guy twice. We have to take the overlap away. Do y'all see where this sort of thing is coming from? If we have something that overlaps, we have to take the overlap away is the basic sort of thing on this. And so this is going to give me 17 out of 52. So that's the 17 if I add both of those sets together, but I've accounted for the overlap one too many times out of 52. 16 out of 52 reduces to what, 8 out of 26, which 4 out of 4/13. Is that right? Yeah, that's right. 4/13 or like 0.3077. Somewhere around there. Are there any questions about these two? And like I would like really compare and contrast like 25 and 26, right? I think they kind of get at the heart of like what the OR statement does. And how to differentiate the overlap versus the non-overlapping sets, right? And with the end statements, 13 and 19 are really the two like I would might maybe probably focus on. Like, are we doing independent things versus are we doing something that's going to influence the next thing, right? Are they independent or dependent? Are they overlapping or non-overlapping? Are the questions we need to be asking. So 39 is what we're on now. Use the method of your choice to determine the following probabilities. Drawing 4 spades in a row from a standard deck of cards when the drawn card is not returned to the deck each time. So we're drawing 4 spades. What's the probability of drawing the first spade?
$13 out of 52.
13 out of 52. And then what would be my probability of drawing a second spade? So if I don't replace the card, how many cards do I have in the deck now?
$51.
Yes, I'm going down a card each time. I'm picking out a card, 51, 50, and 49. And if I want to know how many spades I have left in the deck, after I draw 1 spade out, I'm going to have
12?
12 spades. And then I'll go down to what, 11 and 10. So this, they're doing the same thing over and over again. So the top is also going down. They could technically give me something else, like drawing 3 spades and then a heart, right? And this last one would be like 13 over 49 because I hadn't drawn out any hearts. So they could change things up a little bit, maybe doing something crazy like that. But they're doing all the same cards, so the top should also be going down 1 by 1 each time. So yeah, I don't know what to tell you besides look out for maybe something. I'm not sure if they give you, I haven't seen the other one come up yet in this class, but that doesn't mean it doesn't come up in reality, right? Okay, so these are going to be rather large numbers, but we've done a few of these. We're going to multiply the top through, multiply the bottom through. 497,400. I'm going 17160 divided by that crazy thing. It says it reduces down to 11 over 4165, which is not a pretty number. But if you want a decimal approximation, 0.00264. Which one is this? This is what, 39? They say 11 out of 4165 is what they say. So that's not a pretty number. But this is almost what was that a flush when you have all the same suit? I think 5 cards would be a flush, right?
I
Yeah,
feel
I
like
know.
Christopher's your man for that.
Yeah, 5 cards is a flush. You're right.
Yeah, 5 cards of all the same suits, a flush
Yes.
is pretty high ranking card, right? Pretty
Yeah.
high ranking hand.
You have to have the high ranking. Yeah.
Yeah, so it is pretty rare, right? It's less than 1%, less than 0.2% of the time are you going to get that. I looked over the hands like the other night, going over this. I already forgot them.
I think when COVID is over, I'm going to Vegas and do the poker championship because man, it's killing.
All right, so we got a few more. What do we got? 41. Okay. 41, drawn either a face card, Jack, King, Queen, or a club from a standard deck of cards. So this is an or statement. So for drawing a face card, a Jack, Queen, or King, we've got 3 of them, and then we got 4 suits. I think there are a total of what, 12 face cards? So if there's 12 face cards, what's the probability of drawing a face card? 12 out of
52.
12 out of 52. And drawing a club from a standard deck of cards, what is the probability of that?
12, same thing. Oh well, okay, yeah.
There's 13 clubs.
Yeah, 13 clubs, yeah.
And if I get this, and I add these probabilities together, I'm going to miss one thing because I didn't ask myself. Is there an overlap? Can things
Yes.
be both a club and a face card?
Yes.
And how many things are both a club and a face card?
How many? Say that again.
How many things are both a club and a face card?
12. It's a face card, right?
How many things are both a club and a face card at the same time?
Oh, club and a face. 10.
So a club
Yeah.
and a jack, a club and a queen, and a club and a king is what I'm thinking.
That's
about,
3.
right? There are 3 of them. There are 3 clubs that are a face card out of a total of 52. So I have to take away the intersection. All right, if you wanted to circle your sets, if you wanted to come back to this thing and circle your sets, that might be a good thing to do. I'm circling all the face cards. I'm circling all the clubs. I count up how many cards I have circled, right? You should have, what is this, 25? Out of 52, sorry. And we're going to subtract 3 from that. Should be what, 22 out of 52 is how many you should have had circled if you did that. Okay, if we do 2 and 2 out of 52, I think that's probably what they're going to have in the back of the book. But that is what, around 42%. 0.423, somewhere in that ballpark. Okay. Purchasing 5 winning lottery tickets in a row when each ticket has a 1 in 8 chance of winning. So is this probability going to get larger or smaller than 1/8? Is probably the question that you're going to ask yourself. If I'm purchasing 5 in a row and they're all winning,
Smaller.
it's going to be smaller. So I'm going to do 1/8, and guess how many times I'm going to do 1/8? Is winning on the first one going to affect me winning on the second one? Going to affect me winning on the third or fourth? They are all independent, right? Is what I'm trying to get at. And they're all going to be 1/8. So I should be doing what, 1/8 And I should be doing it 5 separate times. Which is a really small number. Point, and it's giving me 4 zeros. 1, 2, 3, 4, 305. Somewhere in this ballpark. Is what I'm getting from this thing. This is what, 47? 8 to the 5th is 32,768. So they did 1 out of 32,768 is this is going to happen. So probably more likely to get struck by lightning or something, probably. Maybe slightly less. Wouldn't plan on it. Does it happen sometimes in reality? Probably, right? 4 rainy days in a row when the forecast calls for 40% chance of rain each day. And here they're probably making the assumption, even if they don't say it, they're probably making the assumption that rain on one day is not going to affect rain the next day. With that said, are they independent or dependent then?
Independent?
They're independent. So we're going to do 40% how many times?
4?
4 times. So if I do 40 and 40 and 40 and 40.
Professor, why you can't do 40 times 4?
This is not 40 times 4. This is 40 times 40 times 40 times 40. Or you could do 0.4 to the 4 if you're going to do exponents, but it's not times 4. If they're being added, that would be multiplication. So I'm getting somewhere around 2.56%.
That's correct. 0.256.
Mm.
Sorry, 0.0256.
0.0256 is what, 48? Oh, never mind. It's not in the back. Okay. So that's 48, 51, 53. I think these are they're all kind of repeats of ands and or statements, right? They're trying to get you to practice these things, see if you can do them on your own. If it's an and statement, is one of them affecting the other? Am I taking something out of a bag without replacement? Am I taking some people from a group without replacing the people back into the group? Those would be things that are dependent, and I have to change my percentage on, right? Change my probability. Independent would be things I don't have to change. It is like 537, so if you got to get places, you can go and get places. But I got like 3 more problems here, I believe. I got to get through, so I will get through these 3 problems. Randomly meeting either a woman or a Republican in a group that consists of 30 Democrats, 20 Republican men, 50 Democratic women, and 60 Republicans. So how many is this? 30 and 20 and 50 and 60. 30 and 20 and 50 and 60. It looks like there's 160 people. Did I do that right? One of the things you might want to find here is how many people we're talking about total. And so if they want to know randomly meeting a woman or a Republican, how many times is that going to occur? So the chances of meeting a woman is what? There's a few ways we could do this too.
Is it 110?
Yes, if you're looking at women, it would be 110 out of 160. If we want to meet a Republican, what would that be?
Republican would be just a,
I'm seeing 60 and 20.
that's 90 over 160.
6, 7, 8, it'd be 80. 6 and 20 would be 80.
Oh, 30-20. Wait, hold on.
And what do I have to do if I do this? If I add these two together? And like I said, there's a few different ways to do this. You could probably just look at things and see whether they're a woman or Republican and add them up without looking at it, right? Probably could have said this is Republicans, this is women, this is Republicans, and we probably could have added these three up. But if we don't do that, we added up this set, we added up this set. We counted an overlap twice. And so I have to look at things that are both Republican and women, which would be what, 60? So this would be one of those things that overlaps. And so whether I do 110 plus 80 minus 60, I should be getting 130. I think the other way I could do this is by going. Someone vacuuming? What's going on? That's a lot of feedback. Okay. So if I want to do either women or Republican, I can also look here. I got 20 that are Republican. I got 50 that are women, and I got 60. I think 20 and 50 and 60 will also give me it. 20, 50, and 60. Each out of them 160. Should also give me the same thing if I wanted to add those three groups together. Anyway, it should be 130 out of what? 16 or 13/16. 0.8125, I think is what the decimal is. The exact decimal. We're gonna have to approximate this one. Any questions? All right, Miranda meeting a 3-child family with either all boy or all girl children. So it's, if we're looking at this, this is an or statement. So we're asking ourselves, can this overlap? Can they both be all girls and all boys at the same time? No, these things are mutually exclusive. So I think we're safe in saying if we got 3 children, we talked about this, but an all boy family is going to occur 1/8 of the time. And an all girl family is going to occur one out of the 8 times. So if you want to know one or the other, I think it's going to occur 2 out of the 8 times or 1/4 of the time. And so if you wanted to go look at the set of all the outcomes with a 3-child family, that might also help you on this one. 2 of them, one of them is going to be all boys, one of them is going to be all girls. So 2 out of the 8 will be either all boy or all girl, or 1/4 of them will be. The other 2 will be mixed, right? Is what they're saying. Or the other 3. 3/4 of them. Okay. All right, so the last one-on-one free throws. A basketball player is fouled in a one-on-one situation, meaning she is awarded 2 free throws only if she makes the first free throw. Her season average for free throws is 70%. Using her season average as a relative frequency probability, find the probability that she will miss her first free throw. Okay, so I think this is the formula, that Chevalier example that they were talking about. But on 65 part A, maybe hopefully straightforward. If she has a 70% of making the free throw on the first one, what is the chance that she will miss her first free throw?
Would it be 30%?
It's the 30% or the 0.3 that they're talking about on this thing. That's exactly it. What is the probability that she will make her first free throw and then miss her second? One of them is going to make. One of them is going to. So the probability she will make it is what, 0.7, I believe. Probability she will miss is the 0.3. And if we want to know the probability of these two things combined, what are we doing with these two numbers?
Multiply.
Multiplying them, that's exactly what we're doing. We're doing 0.21 there. All right, and then I think C is the final one. Probability she will make both free throws. So if she's going to make it, That's what, 0.7 by 0.7. I believe that's 0.49. So which one is more likely, that she's going to make it twice or miss it? Make it and miss it.
The make.
The make. She's going to make it twice. She's more likely to make it twice. Which should hopefully make sense because she's got a 70% chance of making this thing. The odds are she will make them, right? All right, so that's it. If y'all got any questions, I'll be around. Welcome's more likely. That one's got the better odds, right? Okay, that's it.